Ladies and gentlemen, it's an absolute delight to be with you here at Geotechnical Frontiers, a very successful conference, as you've just heard. And I feel very honored to have been invited to present this, the 53rd Karl Terzaghi Lecture on protecting the environment with geosynthetics. It's a very humbling and rather daunting experience to be following 52 such distinguished past lecturers, including the 4 shown here, who've previously discussed geosynthetics. Like many past lecturers, and indeed the example of Dr. Terzaghi himself, this lecture follows from fundamentals to application. My topic is very broad. Geosynthetics are used in so many different ways to protect the environment. But to keep it to 60 minutes, tonight I'm going to focus on their use in bottom liners to minimize the leakage or loss of water, and particularly contaminated water, to the environment. Geomembranes can be used alone or together with clay to form a composite liner. Now, geomembranes have successfully protected the environment for over 30 years. However, the challenge we still face today is addressing all of the factors needed to ensure good long-term performance, some of which I will discuss this evening. All of the topics I will discuss arose out of field observations and problems, and they all involved scientific research, both theoretical and experimental, in the laboratory and the field, and led back to field applications. This slide highlights a geomembrane in a seam, a cover above it, and a liner below it. These are the key characters in our story this evening. So let's meet them. Gravel, be it angular, uniform gravel or rounded, is often used in drainage layers in many applications, and sometimes it is separated from the geomembrane by a geotextile protection layer. Then we have the geomembrane, and environmental applications. This is most commonly a 1.5 to 2.5 millimeter thick high-density polyethylene, and it is going to be often resting on a geosynthetic clay liner, or GCL, typically 5 to 10 millimeters thick, layer of bentonite clay sandwiched between 2 geotextiles. It is needle punched together frequently and comes off the roll with a relatively low hydraulic conductivity of around 5 times 10 to the minus 11 meters per second. If the geomembrane is placed directly on the GCL, we have what's called a composite or composite liner. Alternatively, however, the geomembrane can be placed on a compacted clay liner with a hydraulic conductivity of 10 to the minus 9 meters per second or less to form a composite liner. Now, GCLs are a manufactured product. They come in rolls, they're laid out in the field with an overlap to provide a seal between the panels. And likewise, the geomembrane comes in a roll, it's laid out, but in this case, it is mostly dual wedge welded to provide a good seam between the adjacent panels. So now we've met the major players, let's start by looking at a geomembrane used on its own and ask how there is an interaction between the cover and the subgrade and how that might affect leakage through the geomembrane. And the first point to keep in mind is that geomembranes are excellent barriers to most fluids, be they liquids or gases, if there are no holes. However, holes can occur during construction, with the placement of the cover soil, and post-construction, both in the shorter and longer term. Now, designers recognize this and typically design with somewhere around 2.5 to 10 holes per hectare. And in the presentation this evening, I'll give some numerical examples where I will assume 5 holes per hectare, where the holes have a median hole size of 10 millimetres. Holes that occur during construction can often be detected, especially if you have a leak detection survey and good construction quality assurance, and can be repaired before the liner goes into service. Much more challenging are the holes that occur as the material is placed above the barrier system, and they may occur in the shorter term or in the longer term. The magnitude of the number of holes that occur post-construction and the strains that could eventually become holes will depend on the pressure, the temperature, time. It'll depend on the type of geomembrane, in particular, its thickness and durability. It will depend on the materials above and below the geomembrane and the efficacy of any protection layer. Now, isolated stones in a clay liner, for example, can be quite problematic in and of themselves. They can cause problems in the shorter term, but hopefully that will be detected. Much more challenging is the holes that occur as significant loads are placed on top of them. And it's not all that easy to actually study holes when you have 10 to 100 meters of material on top of it. But what we can do is we can simulate this in the laboratory with large geosynthetic liner longevity simulators, or GCLS as I refer to them. Large steel cells 0.6 to 1 meter in diameter, in which we can construct a subgrade, we can place a geomembrane, we can place a cover soil, we can seal it up, as you see happening on the right, and apply pressures up to 3,000 kilopascals. And then on disassembly, we can inspect the number of short-term punctures, but equally important is looking at the magnitude of the strains, because if they're too large, they will ultimately become ruptures. To illustrate this, let us look at a couple of examples. Let's begin with a fairly tough case. We've got a gravel subgrade S1, we've got a 1.5 millimeter geomembrane, and then a gravelly cover material on top of it, with the grading curves you can see to the left. And if we apply 2,000 kilopascal load for 100 hours and unload it, even with this short-term loading, we find ourselves with 9 holes in a 0.6 meter or 2 foot diameter sample. That doesn't sound like too much until you translate it into holes per hectare. And it's around 320,000 holes per hectare, somewhat more than 2.5 to 10. Now, it turns out, and this is the point of this story, that that is related in part to the subgrade. So here's with the same cover soil, but a subgrade with a D20 of about 0.1 millimeter, and we find we're reduced to 5 holes. But what is particularly interesting is that if we take another subgrade with exactly the same maximum particle size and the same D20, but more well graded, we have no holes. So it highlights the importance of the grain size distribution of your subgrade. Now, while this has no holes, that's good news, but because the coarse cover soil is on the geomembrane directly, we still have strains of 13%. And as I'll show you towards the end of this lecture, ruptures will occur at strains of more than around 6%, and possibly even a bit below that. So in summary, isolated stones in a fine-grade subgrade may be just as bad or worse than a packed gravel. Punctures likely when we have a gap-graded cover and subgrade in contact with a geomembrane. And even if we have no puncture, if we have a coarse gravel in contact with our geomembrane, we can expect large strains, which ultimately will be problematic. And finally, the shape of the grading curve has a much greater influence than the maximum particle size. So having recognized that the holes can occur, let's consider how much leakage can occur. And of course that will depend on the number and size of holes, but it will also depend on the height of fluid above the geomembrane or head, and we might expect it will depend on the hydraulic conductivity of the cover and the subgrade. A geomembrane used on its own to retain water, as you see in the left here, or it could be used with a thin cover soil, 0.3 to 0.5 meters typically of granular material, as you see in the hydro dam on the right. Now both of these applications are containing potable water, and the acceptable leakage when we're containing potable water is likely to be far greater than in this case where we have a highly concentrated brine solution. So let's explore the leakage that can occur to set the scene for where we're going in this lecture. So let's suppose we have 5 meters of fluid above our geomembrane. We have a permeable drain below it. Perhaps this is the pond we saw a moment ago. If we have our 5 10-millimeter diameter holes per hectare, our leakage is about 200,000 litres per hectare per day, or about 20,000 gallons per acre per day. Now perhaps that means a little bit more if you think about what it is in terms of the drop in water level. And it corresponds to about 20 millimetres or 3/4 of an inch per day. In a dam, probably not a big issue. If that was leaking into the ground from a brine pond, that is a different matter. Now suppose the subgrade below it was 10 to the minus 4 meters per second. We see here that the leakage is unchanged. That is effectively a good drain. But if we drop it to 10 to the minus 6, we're now starting to have some effect. We're now down to 80,000 litres per hectare. Now in this example, I have been looking at the fluid with no cover above the geomembrane. But as we saw in that hydro dam a few moments ago, there could be 0.3 meters of a sandy material, for example, with a hydraulic conductivity of 10 to the minus 5. And if we have the same subgrade at 10 to the minus 6, we only see a marginal decrease in leakage to 70,000. But if the subgrade were 10 to the minus 8 meters per second, then we see a big difference. We drop almost 2 orders of magnitude to 800 litres per hectare per day. So the point here is that the hydraulic conductivity of the subgrade matters. But so far we've pretty much ignored what's above the geomembrane. However, there are many applications like tailing storage facilities where you could have 100 to 200 meters of relatively low permeability tailings above the geomembrane. So let's explore that. And again, it's difficult to do that in the field, but we can simulate it in our GCLSs. We can put in the subgrade with a relatively high hydraulic conductivity. We can place our geomembrane with a hole. We're going to look at 10 millimeters in diameter. We can place our tailings, actually from a tailings facility. We can apply the stresses relevant to the particular case and the high heads relative to the case. And we've done many such tests, and I'm going to only report 2 here, where we've got a subgrade with approximately 10 to the minus 6 meters per second, like we looked at a moment ago. And we have multiplied the results from one test by 5 to give us 5 holes per hectare. And we see that with tailings at a hydraulic conductivity of 10 to the minus 7, we're down to 26 litres per hectare per day, even with 150 metres ahead. And if that drops to 3 times 10 to the minus 8 metres per second, we're down to 2.5 litres per hectare per day. So what is in contact with the geomembrane has a tremendous potential effect on the leakage. As summarised here, if we have 5 10-millimetre diameter holes, 5 metres of pond, we have a large leakage unless we get a subgrade below 10 to the minus 6 meters per second. And we really start to see a benefit if we drop to 10 to the minus 8. But if we have 150 meters of tailings above it, even with that same permeable subgrade of 10 to the minus 6, we have a very low leakage. Now, if a 10 to the minus 8 subgrade is good, a clay liner, which by definition has a hydraulic conductivity less than 10 to the minus 9, has got to be a lot better. And indeed it is. Of course, the leakage will still depend on the number and size of holes and the head. It will still depend on the hydraulic conductivity of the clay liner. But we have a couple of extra things to think about here. Firstly, once we get to clay liner hydraulic conductivity, there is an interface between the geomembrane and the clay that is likely more permeable than the clay liner itself. And it's what we call a transmissive interface, which has a transmissivity theta. And that allows water to migrate laterally at that interface. Even so, if we had our 5-10 millimeter holes per hectare, if the liner was in direct contact with the geomembrane, with the GCL or compacted clay, the leakage would be negligibly small. But there is another factor we need to think about, and that is wrinkles. So in a moment, we're going to talk about composite liners, but just to set the scene, we all know that plastic holds water very well, unless it has a hole. But if we believe the calculations we just saw a few moments ago, then we can anticipate that if there's nothing resisting that flow, that bottle will empty very quickly. So now let's wrap a geotextile around the bottle with a hydraulic conductivity of 10 to the minus 4. And what we see is that it doesn't look as dramatic because the flow is in the plane of the geotextile and running down the side of the bottle, but the water is dropping just as quickly. But if I put some bentonite in with that geotextile to simulate a GCL, we could sit here for a boring hour and see nothing happen. That is why we use composite liners. They can be very effective. And here we see a composite liner being built at the Queen's Environmental Test Site, or QELTS, which I'll talk about several times in this presentation. We see GCLs being placed, geomembranes going on top, and it looks remarkably simple. But in fact, composite liners and barrier systems in general are quite complex, and proper design and construction are essential. Now, to make that point, let's begin with a typical section out of an engineered drawing, where we see a geomembrane as a nice straight line in direct contact with a geosynthetic clay liner. And this is what is often assumed by designers in doing that calculation of leakage, whether using the Giroux equation directly or as it's implemented in the well-known HELP model. And indeed, that can be achieved. Here you see a photograph at our QELTS site on a cloudy November morning when the ambient temperature is 3 degrees, and that geomembrane is beautiful and flat and looks exactly like it does on the design section. But there is a problem. And the problem is that although the calculated leakage is very small, when you actually look at the observed leakages through composite liner systems, they're 10 to 10,000 times larger than what is predicted with a reasonable number of holes per hectare. So why is that so? And it's not that the equation is wrong, it is that the assumption of direct contact was wrong. Here is exactly the same geomembrane at the QELTS site that you saw a moment ago. On exactly the same day, a few hours later, when the ambient temperature is 17 degrees, not all that hot, Celsius, but it is sunny. And that sun is shining on the geomembrane and it is heated to 45 degrees Celsius. That causes the plastic to expand. And where does it go? It goes into forming wrinkles. And here you can see the wrinkles join up and the individual wrinkles very quickly become a long interconnected wrinkle. So if we fly our blimp over a site and take a photograph from 30 meters, you can see the connected wrinkles. There's a whole lot of individual wrinkles that are hydraulically connected. And if we connect them up, we get this network. And so if you have a hole in any point in this network, or even close to a wrinkle, that fluid can migrate with very little resistance over the rest of the clay liner below the wrinkle network. So what are the length of wrinkles? Well, the answer to that question depends very much on the weather conditions, and in particular on the time and nature of the day. So to illustrate that, let's go to the city of Barrie, just north of Toronto in Ontario, latitude 44 degrees north, and let's monitor the length of wrinkles, in fact the longest interconnected wrinkle, with time of day. And you can see that if we were to cover it before 9 o'clock in the morning or after 5 o'clock in the afternoon, our longest wrinkle would be about 200 meters or 660 feet. I want you to remember the timing that goes with that, because I'm going to come back to that 200 meters in an example. And if we were to cover it before 10 in the morning or after 4 in the afternoon, our longest wrinkle would be 1,000 meters, or about 3,300 feet. I'll come back to that too. And of course, if we cover it towards midday, we will get much longer wrinkles. Between 11:30 in the morning and 2:30 in the afternoon, we're looking at in excess of 2,000 meters and up to 2,500 meters, or 1.6 miles of interconnected wrinkle. And this is a relatively small site. Now, what is critical is not what is the wrinkle at any random time of day, but what is the wrinkle at the time you cover it? That is the critical thing, because that wrinkle gets locked in. It may get a little smaller, but it doesn't go away. Now, if you wanted to know what is the maximum wrinkle I could accept, the answer is it depends. It depends on what your allowable leakage is, for example. And you can calculate fairly easily what the leakage will be for a wrinkle network with a wrinkle of width 2b and length L. You can imagine that if it has a hole, then the leakage through the clay liner will be given by Darcy's law. All geotechnical engineers know how to deal with that. What is less expected, but is very important, is that there is also a lateral flow QH in the interface between the geomembrane and the clay. And that lateral flow will be equal to the length of the interconnected wrinkle times the transmissivity of the interface times the horizontal gradient. So with that in mind, we can calculate the total leakage. It will be given by Darcy's law beneath the wrinkle, so that's the area, which is the width times the length of the wrinkle, times the hydraulic conductivity, times the hydraulic gradient, or the change in head over the thickness of the liner. And we have transmissive zones on either side of the wrinkle, so we have 2 QH. And if we substitute for QH, we get a relatively simple equation. Length is a function, of course, width 2b is a function, hydraulic conductivity of the liner is a function, and the thickness of the liner, but the new character here is the transmissivity of the interface theta. And then we have at the end hydraulic gradient. So with that as background, let's go back and look at field data and see what it tells us. Well, the first thing it tells us is not very surprising. The leakage through composite liners is much less than a single geomembrane. Well, think back to the water bottle. The second thing we note, though, is a little bit more surprising. And that is that composite liners with GCLs perform 10 to 100 times better than composite liners with a compacted clay. And you might well ask, why is that so? Well, the answer is the transmissivity of the interface. For a geomembrane GCL, the transmissivity is about 2 times 10 to the minus 11 meters squared per second. Whereas for compacted clay, it is typically in the 2 to the minus 8 to the 1 times 10 to the minus 7 range. In other words, the interface transmissivity with compacted clay is 1,000 to 10,000 times higher. So even though in the equation we take the square root of transmissivity, that translates into a big effect. And that explains, in large part, the difference in performance. So let's illustrate that with some numerical examples. And now instead of a pond, we're going to look at a landfill. We'll take a leachate head, typical design value of 0.3 meters. And to give us context for the discussion, let's first of all assume we have a geomembrane with 5 holes per hectare. And if it was a geomembrane alone, our leakage would be 63,000 litres per hectare per day. Alternatively, if we used a compacted clay alone, with a hydraulic conductivity of 10 to the minus 9 meters per second, 0.6 meters or 2 feet thick, then the leakage would be 1,300 litres per hectare per day. Now let's look at a composite liner with compacted clay and a relatively poor interface, transmissivity of 1 times 10 to the minus 7, a wrinkle of width 2b, and ask ourselves at what length of wrinkle does it really become problematic? And the answer to that question is that we will get some composite liner advantage. In other words, a leakage less than you get with compacted clay alone, provided that wrinkle is less than 640 meters. Once it gets to 640, there's enough spread out of fluid between the geomembrane and the clay that we have lost our composite liner action. Now that's a very bad example in that it means somebody was not being careful in constructing their clay liner. Let's assume that they have a good base and look at a more optimistic hydraulic conductivity, transmissivity of 2 times 10 to the minus 8. And in this case, if we have a 1,000 meter long wrinkle, that was at our site in Barry, covering it before 10 in the morning or after 4 in the afternoon, we've dropped the leakage by about 400 litres per hectare per day. If we were to cover it before 9 in the morning or after 5 in the afternoon on that particular day, we would have dropped it to less than 200 litres per hectare per day. Now we're starting to talk about having a real benefit. So what if we used a GCL? Now for the same 1,000 metre wrinkle, we're at less than 50 litres per hectare per day, and if we can get down to 200, we're at less than 10. Once we get into this zone, it is likely the diffusion of volatile organics from a landfill through the liner system that controls rather than leakage. These are small leakages. But so far, if you notice the fine print, I've said that our compacted clay had minimal or minor desiccation. But in fact, it's not that easy to build a compacted clay without desiccation, particularly if it's an active clay. Now, preventing it before you put the geomembrane on, that's fairly practical. What is much more difficult is preventing it after the geomembrane goes over it. And if that upper surface of the clay desiccates, you still have most of the compacted clay liner. So from a hydraulic conductivity perspective, you're still okay. But your transmissivity has got so high that any leak through the geomembrane is spreading itself out over the entire compacted clay through the network of desiccations, and you're back to having lost your composite liner advantage. So in summary, GCLs reduce leakage compared to compacted clay. Wrinkles will increase leakage and should be minimized at the time of day that you cover it, especially if you have a compacted clay liner. Do not place a geotextile between a geomembrane and compacted clay. It doesn't solve any problems, it just creates them you've introduced a transmissive zone. Desiccation of compacted clay can significantly increase composite liner leakage. Now, we can reduce wrinkles and slow down desiccation by using a white geomembrane, but particularly desiccation can still be a problem. If you really want to use a compacted clay and you have concerns about desiccation, consider putting a GCL between the compacted clay and the geomembrane to minimize the effect. So I hope by this point I've convinced you that a composite liner with a GCL can give you very low leakage. But we can't be complacent. For example, GCL manufacturers recommend that GCLs be covered by 0.3 metre of ballast soil in a timely manner. Unfortunately, this is a recommendation more honoured in the breach than the observance, with composite liners, especially on slopes, often being left for months and in some cases years before they're covered. Now, we built Quelz 1 to explore the implications of leaving composite liners exposed. And we were particularly interested in the issue of shrinkage. And that's what we were focused on. But I'm not going to talk about that today. What I'm going to talk about is what we did not expect. And we didn't even discover it for 3.7 years, because that was the first time we actually cut the geomembrane open and folded it back and looked at the GCL. And what did we find? We found that all 4 different GCLs, all commonly used ones in North America, had experienced downslope bentonite erosion. And we managed to establish that that all occurred in a year. So what is downslope erosion? Well, let me explain. GCLs are expected to and do take up moisture from the subgrade. They hydrate. That's what they're supposed to do. And even north of Kingston in Ontario, in the summer, our geomembrane goes from about 15 degrees Celsius at night to 60 degrees when the sun is shining. That heat not only causes wrinkles, it causes water to evaporate from the GCL. And that moisture migrates to where most of the airspace is, and that is the wrinkles. And then at night, on cooling, that vapor condenses. And since the geomembrane cools faster than the GCL and underlying subgrade, that water forms a trickle that drips, 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 drips on top of the GCL. And that is distilled water. It's evaporated water, it's distilled water. And as it drips down, it erodes bentonite from between the geotextile panels. As you see here, the bentonite is gone. And where has it gone? To the bottom of the slope. But that was not at all obvious until it was opened. So that prompted us to build Quelz 2, which we built with a control section identical to Quelz 1, with a black geomembrane. We used the same GCL with a white geomembrane. We used the same liner system, but doing what the manufacturer recommended and putting on 0.3 metres of cover in a timely manner. And we tested 4 other GCLs we hadn't previously examined. Well, what we found from the control section is exactly what we expected. The whole process was reproducible, and here you can see one downslope wrinkle at the top of a slope, 1.4 metres long and 30 centimetres wide. And you can see that most clearly when we put a light table underneath it in a dark room on the right-hand side. The light is shining through the geotextile where there's no bentonite, and it's black where we have good hydrated bentonite. It turns out you can actually approximately simulate this in the laboratory by taking a GCL, and very importantly, it has to go through one wet-dry cycle before this becomes an issue. And then we drip distilled water on it for 8 hours, and then we let it dry for 16 hours. So a cycle was 24 hours or 1 day. I'm going to show you some time-lapse photography over 7 cycles. When I start it, you will see a rivulet forming where the drops are being dripped onto the surface. And in step 6, or cycle 6, you will see that we have begun to form an erosion feature. And in step 7, we have a major erosion feature. So let's see that. So you can see in 7 steps here, we have gone from having a nice continuous layer of bentonite to having a 70 millimeters or almost 3-inch gap with no bentonite. Now, I want to emphasize that this doesn't happen with all GCLs. Some GCLs, if left uncovered in a composite liner, experience bentonite erosion, and you are very unlikely to detect that unless you open it up and take a look. But downslope erosion depends on a number of variables, depends on site conditions, on the type of GCL, and the length of time exposed. Some GCLs covered by a black geomembrane eroded in 6 months at our Quelt site, and we had major features in 12 months. But this rate will be different at different sites. One thing that's almost certain to be the same, though, is it doesn't happen unless you have at least one wet-dry cycle. So you've got to leave it exposed long enough to get fairly well hydrated in the first place and then dry out. And interestingly, it only happens with distilled water. We ran a test for a year with tap water, no erosion. We ran it with municipal solid waste leachate, no erosion. We ran it with groundwater, no erosion. Only when there's no cations in the water. White did help. It prolonged the time to erosion. We also found that not all bentonites are equal. Some GCLs were far more resistant to downslope erosion than others. But particularly successful was a polymer-coated or multi-component GCL because it cut off the mechanism that causes downslope erosion. But actually the best solution is to do what the manufacturer recommended in the first place and put on 0.3 meters of gravel in a timely fashion. That also cuts off the mechanism. It prevents both shrinkage and downslope erosion. So GCLs can give less leakage, but we still need care in design, selection, and construction. Composite liners should be covered by a ballast layer in a timely manner. If left exposed, compacted clay liners desiccate and some GCLs shrink or experience downslope erosion. And if they must be left exposed, then you need to use both a white geomembrane and select a GCL which has documented good performance in this regard. So we have now, I hope, established that a well-designed and constructed composite liner, particularly with a GCL, can give you very low leakage. The next question is for how long? And that's really asking, what is the service life of the geomembrane? And that's going to depend on many factors that we'll touch upon. Temperature, the chemistry of the fluid in contact with the geomembrane, the nature of the soils in contact with the geomembrane or nearby, the efficacy of the geotextile protection layer, seams in the geomembrane, the characteristics of the geomembrane itself, and of course, what is below the geomembrane. We begin to answer this question by typically taking some samples, immersing them in the leachate, usually in a jar, and putting them in ovens at different temperatures. And then we take specimens at various times. We monitor the change in properties. And a typical conceptual model that is used for oxidative degradation, which ultimately will cause the end of life for our geomembrane, is to plot the property of interest versus aging time. And the first stage is the antioxidant depletion stage. And during this period, we see a reduction in the antioxidants that are there to protect the geomembrane from oxidative degradation. And we measure that in terms of a quantity we call the oxidative induction time, or OIT. During this time, we do not anticipate and do not see oxidative degradation generally. Then there is a second period of time when the antioxidants are depleted, but we still do not have a measurable change in geomembrane properties due to oxidative degradation. But in third stage, we see changes. And we often define nominal failure, or the time to nominal failure, as the half-life, the time it takes for some property of particular interest, be it the tensile elongation at break or the stress crack resistance, to drop to 50% of its initial value. And there's no question that a 50% drop is significant, but it is not necessarily the service life. So what would we say is the service life? Well, the definition I like is that it's when it no longer serves its original design function. In other words, there are sufficient number of holes or ruptures to allow excessive fluid loss. And in this geomembrane you see here, we've aged it, and it was in a situation where it got 61 cracks or ruptures due to brittle failure in a 0.6 metre specimen. That is 2.2 million holes per hectare. And I hope we can agree that it has probably reached the end of its service life. But what are the factors that influence how long that takes? And the first is, what is the geomembrane? And in particular, the resin and the antioxidants and stabilizers used to protect it. And to illustrate that point, I'm going to look at 3 1.5 millimetre thick HDPE geomembranes in municipal solid waste leachate, but at 85 degrees. And these geomembranes all initially met standard industry requirements, yet product A from manufacturer X reached nominal failure in 14 months. A second product, B, from the same manufacturer took 19 months. And product C from manufacturer Y took 31 months. So there is more than a twofold difference in the time to nominal failure, and therefore likely the service life under similar conditions, just depending on which geomembrane one selects. And that's just for 3 of a much wider range. But the geomembrane is only part of the story. It's important. But equally important, in fact arguably more important, are the exposure conditions. For example, if we leave a geomembrane exposed to UV radiation, wide range in temperature, potential damage from humans and animals and like, we can expect the service life to be shorter than if we properly bury it. Now, since geomembranes are mostly retaining a fluid, that fluid will usually have some chemistry, and we need to consider what that chemical effect will be. To illustrate that, I'm now going to take data from extrapolated aging tests down to 30 degrees Celsius. So we're looking at times to nominal failure projected at 30 degrees Celsius for the same geomembrane in 3 different leachates. We see, if we look at the first stage, the antioxidant depletion, L2 is the more severe. It takes 21 years to deplete the antioxidants compared to 28 for L1, with L3 sitting in the middle. But when we look at the time to nominal failure, we see a very different picture. We see L3 is the most critical, with a time to nominal failure of 53 years, and L2 the least damaging, with a time of 83, or 60% longer. And the reason for this is that different components of the leachate affect different stages in different ways. And so L2 actually had an elevated pH, which accelerated the depletion of antioxidants, but it had very few salts. Whereas L3 has lots of salts, and that affected stages 2 and 3. This is also a good point for me to mention that a geomembrane with the best resistance to one fluid may not necessarily be best for another. It all depends on the compatibility of the chemistry of the leachate and the geomembrane constituents. Now, I just gave you two examples, one at 85 degrees where we talked about time to nominal failure in 14 to 31 months. And I gave you an example at 30 degrees where we talked to time to failure in 53 to over 80 years. Well, that perhaps suggests that temperature is a key player here. So what sort of temperatures can a liner be at? Well, if it's exposed, a very wide range. If it's in a normal municipal solid waste landfill in the methanogenic stage, 30 to 40 degrees. If we add a lot of extra moisture to try and accelerate gas production, it could be 40 to 60 degrees. Ash monofills, just through heat of hydration, 65 to 70 degrees. Some heap leach pads, depending on the process being used, could be 70 to 80. Some unusual landfills, and there was a whole session on this yesterday, 70 to above 85 degrees. And brine ponds, depending on how aggressively we try to reduce the temperature, could be in the 40 to 95 degree range. So let's examine the effect of temperature on the time to nominal failure. And we'll start with Geomembrane M.ASCE, 1.5 millimeters thick, in municipal solid waste leachate. And the time to nominal failure at 60 degrees Celsius is 9 years. And we know that with absolute certainty because we ran the test for 9 years. But we have to project to get it at 40 degrees, and it's 30 years. And at 30 degrees, we project 60 years. So a 30-degree difference in temperature is making a 6-fold difference in the time to nominal failure. Now let's look at a second geomembrane from the same manufacturer, but 2 millimeters thick. And at 60 degrees, it takes 13 years. And again, we know that with certainty. This test has been running 17 years. At 40 degrees, we have to go to projections because I don't think we're going to be around in 120 years, but that's what we're predicting. And at 30 degrees C, 430 years. We're now getting to some quite impressive numbers. But so far, we haven't discussed the issue of the nature of the exposure. And all we've talked about so far is specimens immersed in leachate of some type. And that means it's subject to chemical attack from both sides. However, in a real situation, mostly it will have a liner beneath it or a subgrade, and it's only exposed to chemicals from the top. Now, if we look at those two situations, and we can do tests both ways, we take the same geomembrane and we immerse it in leachate, and we take that geomembrane, we put it in a GCLS, in a liner system with a geotextile protection layer and leachate on top. It takes over twice as long to deplete the antioxidants in the actual liner system than it did in the jars. And if instead of just using a geotextile, we used a 150 millimeter sand protection layer, it now takes 3 times longer. And this ratio will depend on the geomembrane, the leachate, the liner configuration, and the stage of the oxidative degradation. But typically, OIT depletion takes 2 to 4 times longer in a real liner system than it does in that jar test. So the numbers we get from jar tests are very conservative. Now we can make adjustment for that once we've done the test to develop the conversion factors. And if we take that 2 millimeter thick geomembrane we discussed a moment ago, at 60 degrees, it will take 13 years to reach a nominal failure, and we've just seen that number. But if we translate that into a composite liner, it's now 50 years. At 35 degrees, we project 220 years. In a composite liner, that's almost 900 years, if there are negligible tensile strains. So let's talk about strains. And we can examine those again in GLSs by building the liner system with the protection layer of interest and the gravel of interest or whatever subgrade and cover you are interested in, and establish the effective strains. And we're going to look at a number of such examples. And we're going to start with a very extreme case. We're going to take a geomembrane, we'll age it to all the antioxidants depleted, so we're at the end of stage 1. And at that time, our stress crack resistance, which is a measure of the nature of the resin, is 700 hours, which is pretty good. And we monitor how long it takes in a liner system where we have a 580 gram per square metre protection layer, 50 millimetre gravel, 250 kilopascals of stress at 85 degrees, for cracks to appear. And it takes 20 months for one crack, and that's equivalent to 35,000 holes per hectare. But very quickly that increases to 2.2 million holes once the cracking begins. Now that is when we aged it so it had 700 hours of stress crack resistance. Let's take the same geomembrane, but we'll age it further before we put it in the cell. So it's now down to 75 hours, almost a factor of 10 less stress crack resistance. And we repeat that test. Now instead of 20 months, it takes 1 day. So that gives you some idea of how important the stress crack resistance is. And it cracks at about 12% strain. And if we repeat that test at different temperatures, lowering the temperature, it takes longer. It takes about 3 days at 70 degrees and fails at 10% strain. It takes about a month at 55 degrees and fails at 7% strain. And you can see a trend of lower strain with lower temperature. In part, that's simply because the geomembrane gets softer at higher temperatures and strains more. Now, based on this, we could predict that it would take about 7 months at 40 degrees C. Well, as it happens, we've been running that test for almost 6 years, and it still hasn't failed. Our testing has shown that there is something that happens at around 40 degrees C and things suddenly get a lot better than at higher temperatures. And that means that the predictions that we tend to make based on accelerated aging at higher temperatures are likely on the conservative side. Now, coming back to strains, we beat up that poor geomembrane pretty badly by putting it in a load of 250 kPa with a protection layer of 580 grams per square metre. We got strains up to 15%, and it went from a brand new geomembrane to ruptured in less than 3 years. That need not have happened. It happened because we used a typical geotextile that is being used in this application, but is totally inadequate. I showed before that if we'd used a 150 millimetre, and obviously better if it's 300, sand layer, it extended the time it takes just to deplete the antioxidants, but it also reduces the strains. Now, here is a specimen on the right under identical conditions except for the protection layer. And you can see it looks in very good shape. The last thing I want to touch on is seams or wells. These are a very important part of a geomembrane installation. And tests we've been doing where we take a weld and immerse it, and we take the sheet away from the weld and immerse it, show that the time to nominal failure of the geomembrane sheet is about 50% longer than for the weld. Or put another way, the time to nominal failure of the weld is about 67% of that of the sheet material. But that depends on the leachate. If we use a municipal solid waste leachate, the factor is 2.2. Or the failure of the weld is at about 45% of the time for the sheet. Now, the reason for this is twofold. One is because of eccentricity in loading with a weld, which magnifies the strains in the sheet. But the second and most important reason is that the material in what we call a heat-affected zone, right adjacent to the weld, that's not part of the weld itself, is affected by the welding, and it degrades faster than the sheet that wasn't affected by that heat. And that's mostly what you're seeing here. So in summary, we typically have over 1,500 metres of weld per hectare. They are the critical location with respect to service life. Now, the time to failure of wells needs more investigation, but our work so far shows that it depends on the geomembrane, the leachate and temperature, and we're currently looking at how the welding parameters affect it. Now, if you want to minimize the potential effect of a failure in the weld, there are two things you need to do. One is minimize the number of wrinkles at the time the geomembrane is covered. And the second is use a composite liner with a GCL. Both of those things will minimize any negative effects of the ultimate weld failure. So in summary, the geomembrane service life depends on the geomembrane use. That's partly the manufacturer, but it's also the designer who selects the geomembrane. Then it's the exposure conditions, and they've got nothing to do with the manufacturer. They're the designer, construction, and/or operations. And depending on what one does, it can range from a few years to many centuries. So I have covered a lot of ground in the last almost 60 minutes. Let's take a few conclusions. Firstly, what you require as a liner depends on what is your acceptable leakage. A geomembrane alone can be very effective in many applications. If we need to reduce leakage, it can be substantially reduced with a composite liner. GCLs reduce composite liner leakage better than compacted clay. Wrinkles increase leakage for composite liners and should be minimized. And there are tools available and advice available to do that. Do not place a geotextile between a geomembrane and compacted clay liner. Cover composite liners in a timely manner. Desiccation of compacted clay can substantially reduce the effectiveness of a composite liner. And there are many different geomembranes and GCL products out there. They're not all intended for the same purpose. Pick the right material for a given project and exposure conditions. Science and accelerated aging techniques can be used to assess the relative performance of different geomembranes in different environments. And we find from that that a different geomembrane formulation will have a different resistance to degradation in a given leachate. And the same geomembrane can have quite different resistance depending on the chemistry of that leachate. We can also examine service life, and what we find is that the critical issue is tensile strains. We certainly need to keep them if we want a long service life below 5%, and I'm actually a strong supporter of the Germans advocating 3%. Our data is definitely heading in that direction. So when we're designing a barrier system, we need to consider the overall system performance and especially be sure that optimizing one component was not compromising other components. So for example, using a coarse gravel is great for your leachate collection system, but lousy for your geomembrane if you don't put in an adequate protection layer. Our objective should be to minimize the lifetime cost of a project, not the cost of individual components. Too many things go wrong because people are trying to buy the cheapest product they can get their hands on. It costs a lot more to get it right in the long term if you pick the wrong material in the first place. Better to spend more money and get it right the first time. With good design, construction and inspection, geosynthetics can provide excellent long-term performance. And there are ever more new challenges, and they're being addressed by new products and research to provide confidence in their use. Now, I have, in 60 minutes, gone over more than 20 years of work. It would not be possible without many entities providing cash, materials, access to sites, and other forms of assistance that are absolutely critical. Also, while I'm presenting this talk, it's really the work of a large number of people. My collaborating researchers, both the colleagues in the Queen's RMC Geoengineering Centre, and my collaborating researchers in Australia and the US, and a host of postdoctoral fellows, PhD students and master students who actually do all the hard work. And finally, I'd like to thank my family for their patience and for allowing me to do something I love. And I thank you for being here and for listening.